Hi there, welcome to episode 5 of Geometry Nodes inside of Blender. Let me digress a little from our main topic, Geometry Nodes, and let's discuss some fundamentals in this episode. Vectors. Because vector math and vectors is the basis of all 3D, and as we will build more and more complex geometry node setups, we will have to make sure that everybody understands what vectors are and how to work with them. Let me switch over to a geometry nodes editor and create a new node tree, but not because I want to do some geometry nodes. This time I just want to abuse this as a drawing board. So if we talk about vectors, there is two equivalent definitions, an algebraic one and a geometric one. The geometric one is more important to us, but nevertheless I will start with the algebraic one. You probably are familiar with working with standard numbers, one-dimensional numbers like, for example, 1, 5, 6.8, and 7.5. These numbers in a vector math context are called scalars, just to differentiate between normal numbers and vectors. Now, a vector is nothing but a list of numbers, an array, and you write it like this. You just create brackets, and then you write all the numbers that form the vector in these brackets, like, for example, 5 and 8, like so, and then you close the brackets. That would be a two-dimensional vector. But vectors can have arbitrary dimensions. So, for example, I can have a three-dimensional vector consisting of three numbers, 3.8, 2.5, and 6.4, for example. So a vector just means take a list of numbers and treat them as a whole, as one number, a multi-dimensional number. So we can give a name to these numbers. If you give a name to normal numbers, that is called a variable, like for example, a is 1. Now you can do the same thing with vectors. We can say this vector here is called v. And to differentiate between vectors and scalars, we put a little arrow on top of vectors, just to say this is a vector consisting of more numbers. In 2D, we usually work with two-dimensional vectors like this one here, and in 3D, we work with three-dimensional vectors consisting of three numbers. If we look at these vectors in a geometric way, a vector has two properties, a length and a direction. So for simplicity's sake, let's go with 2D vectors. Let's consider the vector 1, 2, for example. Now, if you want to draw it, you first need a coordinate system. So let's create a coordinate system with origin down here and the x-axis and y-axis, like this is the x-axis and the y-axis. Now, this is 1 unit and this is 1 unit, and this is 2 units. Now, by convention, the first component of a vector refers to the x-axis, the second one to the y-axis, and if you are dealing with 3D vectors, the third one means the z-axis. So if you want to plot this vector, you go 1 unit to the right and then 2 units up, x and y. So you end up here. But this is not a vector. This is just a point in the Cartesian plane, in the Cartesian coordinate space. The vector is something else. Let me create a new layer with a different color, like orange. So the vector we just created is this one. This vector here is the vector 1, 2. Let's give it a name. Let's call it P, say, with a little arrow on top. So that is a vector P. Now, very important, although we drew the vector starting at the origin and pointing to this point, this vector has no location. The only property that is important is that it has a length and a direction. And that means if I take any vector with the same length and direction, let me roughly try to draw this like this, for example, that is P2. So these vectors are the same vector. And this is because vectors are not points. Vectors are something relative. Vectors can be seen as encoding a translation, a process, something that is done relative to something else. So if I think of this vector as a movement, for example, then I can say this vector encodes a movement 1 unit in the x direction and 2 units in the y direction. Then you will move from there to there. But a movement is always relative. It is not absolute. A movement only makes sense if you know where to start. And you can start anywhere. And that is why these vectors are the same, because they are encoding the same movement. Now, how are points and vectors related then? Because you already worked with points. Points have coordinates. Coordinates are an array or a list of numbers too. So here, for example, I have a point, and here I have another point in my coordinate system. Well, the relationship between vectors and points is that the vectors are the translation needed to get from the origin to the point. That means Blender and all other 3D DCCs too use vectors to describe where points are located in space. So for example, let me create just another layer. This point's location here is described by the translation P, and this point here is described by this vector here. Let's call it Q. Now, this vector P and the vector Q are called the location vectors of these points, as they are describing where the points are located. Now that we understand the relationship between vectors, translations, and points, locations in space, let's think about what we can do with vectors. Let me move these nodes out of the way again, and let's draw another Cartesian coordinate system here. Fresh drawing. Now let's say we have a point here, and this point has a location vector, this one here. Let's call it P. This is describing the location of this point, and say I have another vector, a vector Q. Now this vector is describing another translation. What we could do is we could chain the translation, starting at the origin, then going all the way along P to reach this point, and then going along Q to reach this point here. Now I chain these two vectors. First I go along P, and then I go along Q. And what we do here is called vector addition. We are adding these two vectors. So to reach this point, we have to first go along P, and then plus Q. First along P, then Q. And then we reach this point. Now what is the result of this operation? It is a third vector. Let's make it yellow. And it is in my case called R. And it is the vector that connects the origin to this endpoint here. This is the vector R because it is equivalent to first going to here, then going to there. So the addition of two vectors is this vector. To find the resulting vector of an addition of two vectors, you first take the first vector, then you put the tail of the second vector to the tip of the first vector, and the point that you reach then is the addition of two vectors. And you can see it in a different light too, because you can of course switch this over, like Q plus P is of course R again. The order of operation does not matter. You can first go along Q and then go along P, and you will reach the same point. So now we have a geometric intuition of what vector addition is. Vector addition means take the vectors, put the tails at the tips, then you form a parallelogram. This parallelogram here, and the diagonal of this parallelogram is the result of the operation. So adding vectors gives this vector in the middle. Now that you understood how vector addition works, let's create a little component inside of Blender to visualize this and play with it interactively.